Hello and welcome back to Let's Code Physics. We are at long last getting back to our police officer chasing the speeding vehicle. We've got a few new things for this episode. For one, I am now in this lovely webcam window that I've been trying out. I'm pretty happy with it, so I think I'm going to stick with that. I have discovered that I can actually gesture now that I have this window. But also at the end of the episode, there's going to be a couple of special announcements. So be sure you stick around through the end of the episode so you can hear the two special announcements. So like I said, we are back to our problem of the police officer chasing the speeder. We have developed our code in Scilab. Just as a refresher, what this code is doing is it's going to create a graph of the speeder's motion. We've assumed that to be a constant velocity, so that's the blue curve that you see on the graph. And the police officer, we've been assuming, has been at a constant acceleration. That's the red curve here. So on a position versus time curve, that produces this nice red parabola. I've made a couple changes to the code just in between episodes. One, I've gone ahead and preloaded some different acceleration functions. They're all commented out right now. So right now, the only acceleration function working is the constant acceleration of 3 meters per second squared. But I've also added in a piece to calculate the maximum acceleration that the police officer experiences. The reason for this is that if we're going to have a variable acceleration for the police officer, we want to make sure that acceleration does not get too high. I just saw The Martian last night and was reminded of, what happens when you reach 12 Gs, which somebody does at some point in the movie. Don't want to give away too much. But, we do want to keep an eye out on that acceleration factor. So acceleration due to gravity, or 1g, is about 10 meters per second squared. And so, we want to divide that number by about 10 to get the approximate g-force. And so the way we're going to set that up is through Scilab's native max function. The way that works is it takes two arguments, and whichever one of them is greater, it returns that one as the maximum between the two. So we just start out with max acceleration police officer equals 0. The max variable gets updated as the maximum between AP and max AP, and then it's going to display max AP down below. Now, AP is always going to be 3 in the code we've been using, in the scenario we've been studying, and so it's just going to display this 3 here at the end. So just as a refresher, police officers catching the speeder after 864 meters and some change in about 24 seconds, and now we're keeping track of the police officer's maximum acceleration. So the reason we want to try some non-constant acceleration functions is because even if the police officer slams onto the accelerator, that is not going to result in a jump from 0 acceleration to 3 meters per second squared. We need something that will get him from 0 up to the maximum that we're interested in. So one way to do that would just be to linearly increase the acceleration with time. That's what I'm doing in this function right here. So I'm taking the maximum, dividing it by the amount of time that it's been taking, 24 seconds, and multiplying that by the time. Now, of course, that means it's going to take longer, as the police officer will be traveling slower. But, this is going to be a nice linear function. Just to confirm that, let's check that over in GNU plot. So GNU plot is a really handy graphing utility. So we're just going to plot 24, other way, 3 divided by 24, 3 over 24 times x. Not 3.24, 3 over 24 times x. There we go. The independent variable is always x, no matter what you call it. Empty y range. That's weird. Integer division. Always put a .0 after things so it doesn't think it's an integer. Right, so that's going to be nice and linear. So this thing is going to integrate this linear function. I think I closed my graph. Yes, I did. I closed my my Scilab graph. So let's compile the code and run it, or save and execute, excuse me. And so the first thing I notice is that it does take the police officer longer. It takes police officer just shy of twice as long, so 24 seconds compared with 41 seconds. You notice also that this has a much broader shape than the parabola did. Since we're integrating This thing is linear, so this thing should be going like the cube, right? Because if I went from constant acceleration to linear acceleration in time, then the position should go from going like t squared to going like t cubed. But what you notice is there's a drastic difference in the distance. So we've gone from 864 meters to 1496 meters. So we've nearly doubled the time, and we've just shy of doubled the distance. What you also notice is that max acceleration that we're now putting in has changed. It's gone from 3 meters per second squared to 5 meters per second squared. So the police officer is now pulling just over half of a G. So that's not entirely pleasant. And of course, what you could do, we could change the factor that's out in front, so we could have the police officer accelerate at a quicker rate. And what I'm going to do here is I'm going to leave this curve on here just to indicate that as the previous curve. So what we're going to do now is we're going to have the police officer accelerate a little bit faster. So instead of accelerating at 3 meters per second squared for every 24 seconds, he's going to accelerate at 1 meter per second squared for every second. So that's much faster. Let's see what that does here. So here's the graph we had before. Here's the graph we have now with the police officer accelerating at a rate of change of 1 meter per second per second per second. That gets, a little tiresome after a while. The time to catch gets cut down to 14 seconds. Distance gets cut down to 530 meters. So that's good. That's a good improvement. But we take a look at this maximum acceleration. That is 14.69. So 14.69, divide that by, let's even use the actual number, 9.8. Police officer is pulling 1.5 Gs at this point. That's not terribly pleasant. That is not a good thing for a police officer to be doing. So what it would be nice to do is, it would be nice to have a function where we could specify what the maximum is. And that's where exponential functions come in handy. So what we've got here is an exponential function. The nice thing about exponential functions is that they've got a minimum value of 0. So when you graph e to the negative something, that means it'll tend to go towards 0. And so if I graph, let me get back over to GNU plot. So that means if I graph 1 minus e to the x, right, is that what I've got over here, is 1 minus e to the negative x. That's a little bit different function. What that means is this piece is going to approach 0, so the whole thing is just going to approach 1. Oh, and we are not interested in negative time, so let's set our x range to be 0 to, let's go out to 30 seconds and replot. So what you see is he's going to start out at 0, and within about 5 seconds it's going to get up pretty close to the maximum value of 1. So let's keep our graphs again. So again, this is the one with the pretty this one with a pretty safe linear acceleration. This one's with a pretty dangerous linear acceleration increase. Let's save and execute. I do not see a new graph. Oh, there it is. It just took a little bit longer. So we get a new graph that's somewhere in between. So this thing is definitely not a parabola or any kind of nice function that we know about because it involves those exponential terms. Let's go back over and check the result. So as expected, the maximum acceleration of the police officer is 1 meter per second squared. The time it took was about 73 seconds, so just over a minute, and we've got 2.6 kilometers here. We can improve on that because basically this function will take on the value, a maximum value of whatever you multiply it by. So if I use this 3 times this function, let's go back over to GNU plot. If I change this now, multiply it by 3, the graph is going to look the same. It's just going to take on a maximum value of 3. So if you compare that to the last one, actually I can compare both of them because I can have 1 minus exponential negative x. See, they're the same graph qualitatively, it's just a matter of what their maximum is. Okay, so let's put in this function. Let's get our console ready and our graph ready so we can see where it comes out. So we should expect this thing to be somewhere, I think, between these two, because the police officer is reaching a lower maximum acceleration. So let's run this. Okay, so we got something in between there. I should probably be using different colors for these, but I'll just keep hovering my mouse over the newest one. So in this one, a police officer is catching up with the speeder in about 25 seconds and about 933 meters. So this is relatively close to our original, because our original was 24 seconds and 860 meters. We're now at 25 seconds and 933 meters. So we're getting about the same amount of time, just a little bit more distance, and we're keeping that maximum acceleration. Now, this model is more physically reasonable because the police officer is getting up to a maximum acceleration. He's going from 0 to that. But of course, this function assumes that the police officer is going from 0, from not moving at all. So imagine a flat line to the left of the graph here, to suddenly having this sharp spike in the acceleration. And even if the police officer pushes on the brake, there's going to be some easing into it. And that's where this really great function comes in called the logistic function. The way this function works is that you've got a maximum value. So again, we're going to use 3 for the maximum. But then you've also got a rate and an offset. And the rate just says how quickly it's going to ramp up to that maximum. For simplicity, we're going to use the rate of 1 and an offset of 1 for right now. So what I'm going to do, I don't want to copy that into GNU plot. There'd be too much to change. Let's plot this thing. Let's plot the original one. So we'll have the original one here. And then I want to use the logistic equation. So this one is going to be 3 divided by 1 plus exponential of negative. We'll just leave that as a 1, x minus 1. All right, I think I've got all my parentheses closed here. Maybe I can resize. Ooh, I can resize my window just enough. So I've got a 3, and I've learned my lesson before to make this a 0.0. And actually, I need to put parentheses around my denominator, don't I? That would be helpful. There we go. My students were just laughing there for about 30 seconds. So we've got a 3 divided by 1 plus exponential negative x minus the offset. Okay, let's take a look at what this function looks like. Close parentheses expected. Oh, I am missing one. Okay, forgot to count those. Okay, so the difference that you'll notice is that the red curve starts out at this sharp spike. The green curve, the logistic function, starts out much smoother. And I thought it was going to start smoother than that. So apparently I need to play around with this offset a little bit more. Apparently I need to play with it a little bit more. Okay, this is getting a little bit better. Let's make this a -6 maybe. Okay. So what the logistic function does is it has this, over to the right, it has the same type of approach up to the asymptote that the 1 minus e to the negative time function does. So that's really nifty. But the way it starts out is it starts out with this flatter tail here. So what I'm going to do is I'm going to change this t0 to a 6. So unlike in the Root Finder episode, I am graphing before I run the code. So I'm coding a little bit more intelligently now. So we've got our rate of 1, we've got our offset of 6, and that's just shifting the green curve over a little bit. So this is going to be the officer's acceleration. I'm now paranoid about integers, so we're just going to make sure that all of those have a 0.0 at the end. The integer thing is basically whenever you divide by an integer or divide an integer, a code can do something funny like chop off the decimal places. So you always just put a .0 afterwards to make sure it's all working out fine. This is starting to get a little cluttered. So what I'm going to do is I'm going to change the police officer. Let's go from blue to red to green, just so that we can see this final one. This will be our last one that we try out today. And then in the next episode in this series, we're going to We're going to try out some different reaction times. And speaking of series, oh wait, I almost gave away the special announcements. You have to stay until the end. So the green is going to be our final one. It's going to be our logistic function. We are going to save and execute. Okay, so again, the maximum acceleration was 3. Police officer catches in 34 seconds in 1255 meters. So it's splitting the difference between these two, between this unsafe acceleration, this unpractical acceleration, impractical, unrealistic acceleration, and between these two, where the acceleration is jumping up at the beginning. So we get something kind of reasonable there at the end. Again, you notice that these curves, they're sort of qualitatively the same. They're all sweeping upward, but they're behaving quantitatively differently. So for example, these two curves, they intersect here. So there's some point at which, if one police officer accelerated this way and one police officer accelerated this way, one of them would pass the other one. So that would be fun to watch. Just to delay things just a little bit to get to that announcement, let's open up the animator and let's take a look at what this logistic function looks like when animated. So I think I want to exit this. And we're going to save and execute. And again, the green represents the speeder. The red represents the police officer. So you notice police officer starting out relatively slowly because that logistic function says that the acceleration is going to gradually ramp up. But then after about so they're going to catch up about here. So around, so around maybe the 1/3 to a halfway point, police officer acceleration is going to ramp up. And this distance, this gap here, is going to close pretty quickly. So right now we're seeing where the police officer's acceleration is picking up. And then he's going to be catching up with the speeder pretty soon here. So you notice that gap is starting to narrow. And almost there. Surely the speeder sees the police officer by now, right? And it is another successful day for local law enforcement and for the logistic function. So thanks so much for watching. Thanks for being patient as we waited to get to the special announcements. So I've got 2 special announcements to give you. One is that on October 28th, there's going to be a special Halloween episode of Let's Code Physics. I thought of this a couple weeks ago, so I've gone ahead and recorded the episode, and it'll be a lot of fun. I'm looking forward to it, and I'm asking for your participation. So I'm having the episode run on October 28th, so that by Halloween, October 31st, you can take the code, do something special with it, and run it, share your results either on YouTube or on Twitter at Let's Code Physics, and then we can flood the internet with this physics Halloween wonderfulness. I'm not going to tell you what it is because you have to watch the episode, but it's something easy, something straightforward, something that you just change the numbers in and you can make something wonderful to share with everybody for Halloween. Second big announcement is that, so apparently I have gained a subscriber following. Thank you to our 600 plus subscribers that have subscribed at this point. So I've taken a suggestion from one of the subscribers who's commented on a previous video, and I'm going to be making a video to say thank you to all of the subscribers. Actually, it'll be another series to say thank you to the subscribers. So be looking for that in November, that special subscriber thank you. So thanks again for watching. I hope you enjoyed it, and I'll see you next time. Bye-bye.